All right, picking up on section 7.2. Got somewhere, I think we're around number 13. So number 13. So the region enclosed by the given curves is rotated about the specified line. Find the volume of the resulting solid. So y equals 1 over x is 1, x is 2, y is 0. So that's our region, and we're doing this about the x-axis. All right, so let's go ahead and start with our drawing. So let me take care of the easy things first. I've got a lot of colored markers here today. So let's try x equals 1. It's going to be here. So x is 1. We've got x is 2. It's over here. I've got y is 0. Let's see, that looks like the other one. Oh well. Y equals 0 is the x-axis. And then we have y equals 1 over x. So at 1, the value of that function is 1. At 2, the value of the function is 1/2. And we know that the function looks like this, goes up, goes like that. So I think it's pretty obvious what the region is. We've got this region right in here. We want to rotate that around the x-axis, which is going to be this axis right here. Well, we're rotating around the x-axis. And I'm going to kind of clean up this side a little bit because I'm going to transpose that rectangle that I'm about to put in there. So we're going to go around the x-axis. We're going to use a method of discs or washers for this. Then my rectangle that I draw is going to be perpendicular to the axis of rotation, noticing that the blue function is always the top edge of the rectangle. The bottom edge of the rectangle is always going to be the x-axis, or y equals 0. So now bringing that over here, we have the blue function on top. We have y equals 0 is the bottom. Our axis of rotation was also here. So what we need to do is determine the outer and inner functions, or distances. So the outer distance is the distance from the axis of rotation to the edge furthest away. That's just the height of that function, that's 1 over x. And then the distance to the inner edge right here is always 0. So that's all we need to set it up. The integrand, now the limits of integration are from 1 to 2, because that's the variation we have there on x. So the setup of this integral is the volume will be pi integral from 1 to 2 of the outer function squared minus the inner function squared dx. So the outer function is, I didn't label this, this is the outer function. This is the inner function. So the outer function, 1 over x squared, and then 0. So this is equal to pi integral 1 to 2. When you square that, you get 1 over x squared. 0's gone, dx, and then the rest of it's pretty clean. All right, moving along. Let's take a look at number 15. I'm waiting for one of these to get hard. Let's see. Okay, we have for 15, x minus y equals 1, y equals x squared minus 4x plus 3, and we're rotating this about y equals 3. All right, so this one looks a little more interesting. So here's my picture. Let's start out with the first one here. We'll do it in red. This one. If I solve this for y, get y equals x minus 1. And that way it's a function of x. And if I graph that, that's a line. It has a y-intercept of negative 1. Has a slope of 1. So it's going to start here, up 1 over 1, draw a straight line. That is y equals x minus 1. The next function I have is a quadratic function. It's a parabola. And so it might be worthwhile if I know how to graph a parabola function. The most important part of this is to understand this is a parabola that opens up, so you know it looks like this. It would be nice if we know the vertex. Vertex, very easy to find. You remember that on a parabola, the slope of the tangent line at the vertex is 0. So if we just take a quick derivative of this, we get y prime equals 2x minus 4. And that's the slope of the tangent line. I want to know where that's 0. So if I set that equal to 0, you get x is 2. So if I go over here to my graph at x equals 2, well, actually I need to find out what the y coordinate is. So let's take that 2 and plug it in here. If we plug in 2, we get 4 minus 4 times 2 is 8 plus 3. So we get negative 4 plus 3 is negative 1. So the vertex, this point right here, is x coordinate 2, y coordinate negative 1. So if I go out to 2, I go down negative 1, I'm right here, and then it should open up. Now I don't need to, but I could also find the x-intercepts to get a better graph. So I could just take the original function and set it equal to 0. So if I factor this out, x minus 3, x minus 1, set that equal to 0, you get two solutions, 3 and 1. So I know I have an x-intercept here, and I know I have an x-intercept here. So when I go to draw this, it goes like this, and over here it goes like this. And you can see that I am going to hit that other line somewhere over here, right there, and I'm going to have to figure out where that is, but I'll do that in a minute. All right, so there, I think we see the region. I hope you see the region that's bounded by those two functions. It's right here. And we're rotating this about the line y equals 3. Now y equals 3 is a horizontal line, and it's moved up 3. So, 1, 2, 3 up here. So I'm rotating around that line. So that region's going to go around this line, and we're going to get some solid. I'm going to use vertical rectangles. So here's an arbitrary rectangle. And I just want to verify that as I move this left and right, the function on top stays the same, which it does, it's the red one. The function on the bottom as I move from left to right is always the blue curve. So the vertical rectangle will work for me. So now what I'll do is I'll determine, I'll transpose things over here. So here's my axis of rotation. Here's my x-axis. My rectangle's in here. I have my blue curve, which is always on the bottom. I have my red curve, which is a line, on the top. And so now I just need to figure out these distances. So I'm rotating around here. All right, so what is the distance from this line all the way down to the outside edge of the rectangle? And then what is the distance from here to the inside edge? So let's talk about the outside first. All right, so the distance from here to here is 3, right? So if I look just here to here, that distance, let me do it in a different color. This one's a little tricky. Distance from here to here is always 3. And then we need to tack on this much. So how much are we gonna actually add on to this? Well, if you think about plugging in the number 2, right? If you plug in the number 2, it's going to spit out -1. So if you plug in 2, it spits out -1. If we were to take 3, we want this distance to actually, like if this rectangle was right here, we would want this distance right here to be 1. So we have 3. If we plug in 2, we get -1. We don't want it to be -1. We actually want it to be +1 because it's a distance. So what we're going to do, this distance right here to here, this is the function. What was the function? It was the parabola x squared minus 4x plus 3. So that's this distance. But you have to be extremely careful here because I don't want to just add it. If I take 3 and I add the function's value, I'm going to add -1, and then that's going to mean that it's actually 2, which it's not. 2 would be up here. So I need to actually subtract this from this to get the signs to switch. I know that's a confusing idea, but it's part of what makes this a little challenging, is you're looking at a distance as opposed to just the function's value. So this distance here should be 3, and then instead of plus this, minus this. Okay, so let me explain again why this is working this way. If I were to go to 2, right, just as an example, then the distance from the axis of rotation up here all the way down to the bottom, okay, so from here all the way down to the bottom would be the 3 that I need to get from here to here, and then the distance from here to here. So if I plug that 2 in to this, you get 4 minus 8 plus 3, that's -1. So if I were to just add this, if I were to do 3 plus this, it would really be 3 minus 1, which I don't want because I want it to be bigger than 3. So I have to subtract that. So it's going to be 3 minus -1, which would be 3 plus 1, which would be 4. And that's what the rectangle would be right here. And then as you move from left to right, because all these values are below the x-axis, the same thing is going to happen. All right, I hope that makes sense. All right, that's going to be the out. Now the in is a little easier. Okay, so you want to know the distance from here to here. We know that the distance from here to here is always 3, and we know the distance from here to here is going to be the height of the line. The line is x minus 1. So our distance is 3, and then we want to take away this much. All right, if we take 3 and we subtract this much, then we'll get this distance. So this, I'm almost off my graph, or almost off the video here. This will be 3, and then we take away the x minus 1. Let me make sure that came out on the video. Yeah, okay. So this is the in. A little tricky. All right, I've got my out, I've got my in. Now let me go back and determine what that point was, because I need to figure out where I'm going to integrate from. I know it starts at 1, just from my picture, because it was pretty good. But I don't know where it stops. So I have to set these two things equal to each other. So I need to set x minus 1 equal to x squared minus 4x plus 3. And then I just move things over. 0 equals x squared minus 5x plus 4. That gives me x minus 4 times x minus 1, which gives me two solutions, 4 and 1. Now I already knew 1 because I had it right here. Now I know that this was 4 over here. All right, so with that I can set up my integral. Got everything I need. The volume of this solid of revolution will be pi integral 1 to 4 and then the outer squared minus the inner squared dx. Now this outer, I didn't do this, I didn't clean it up over here. I'm going to clean it before I go in there. I'm going to distribute the negative through, and you would get 3 minus x squared plus 4x minus 9. And you can combine the 3's together, and if you do 3 take away 9, you get negative 6. So that'll be negative x squared plus 4x minus 6. And then the other one, if you distribute the negative through, you get 3 minus x plus 1. 3 plus 1 is 4, so that's 4 minus x. And that's it. Now, you would have to actually expand this out, FOIL it, and I mean, it would be this times itself, and then here, same thing, and then you're off, you're in business. All right, that one was a little complicated, especially this piece right here. Especially this. Got to think through this a little bit. Your instinct is to just want to take 3 and add this much. It's the fact that it's underneath the x-axis tells you need to subtract it, so that the double negative will turn into the plus you need in order to make the distance greater than 3 as opposed to less than 3. All right. $17. All right, I was waiting for one of these. Y equals x cubed. Y equals root x. We're rotating this about x equals 1. All right, so y equals x cubed. Let me start with the square root of x. That's a little easier to draw. Square root of x starts here. At 1, it's at 1. And then we'll go out 2, 3, 4. At 4, it's at 2. So we got a graph that looks like this. Probably won't need that much graph, but that's what I've got. Okay, and then on the next one, x cubed. At 0, I'm at 0. At 1, I'm at 1. At 2, I'm at 8. And in here, it's going to go like this. On the other side, it does something like that. So I can see my region. This is my region. And we want to rotate it around the line x equals 1. Now, x equals 1 is a vertical line, not a horizontal line. So I want to rotate it around this axis right here. Okay, so I look at this picture, I realize, you know what? I drew it a little too small. I'm going to start over just to give myself some more room to work with here. So I'm going to erase this. We come back in here. Focus a lot of my attention here in that first quadrant, like this. And then I know with the blue one, the square root of x went like this. Let's say that that's 1 right there. And then with the green one, it went like this. Of course, it keeps going, and the blue one keeps going. So this was root x, and the other one was x cubed. But we're trying to rotate this around this line, which was x is 1. And my region here is there. So now there is a technique I can use called the method of shells, which I will talk about in class, but let's try and do this one with the method of washers and discs. So I cannot use a vertical rectangle here. As much as I want to, I can't, because with method of discs and washers, your rectangle has to be perpendicular to your axis of rotation. So here's my axis of rotation, here's my rectangle. They're parallel, not perpendicular. So I have to use a rectangle that goes sideways. Now if I do this, okay, okay? If I use a sideways rectangle, then these functions, the blue one and the green one, have to be functions of y, not functions of x. Right now they're functions of x. So what I need to do is convert these. I need to solve these for x. So I'm going to take the cube root of y, or cube root on both sides, and you get this. And then here I'm going to square both sides and get that. So now you have x in terms of y, x in terms of y. These are both functions of y. So I'm going to come back in here, and the blue one is actually going to be y squared. And the green one is actually cube root of y. And that way I can actually draw this out with the sideways rectangle. All right, so now how do we transpose this? Kind of can go up or down with it. I'm going to go up. Just remember that's our axis of rotation there. It's a little easier for me to draw above this. So I'm going to draw, first of all, my y-axis here. Here's my rectangle. I have the blue function on the left, the green function on the right. My axis of rotation is here. And so I need to get an outer radius and an inner radius. So I stand on the axis of rotation. I look out to the farthest edge of my rectangle, which is right here. I have to figure out that distance. Then I have to figure out the distance from here to here. Well, we know that the distance from here to here, from the y-axis to here, to the blue, is the function of y. So I know that from here to here is y squared. I also know that the distance all the way from here to here has to be 1. So if the distance from here to here is 1, I'm probably off my video, but I think you heard what I said, then this distance here should be that total distance 1 taking away the y squared. So like if this was 1/2, or not 1/2, if this was like 1/8, then this rest of it would be 7/8, and that you get that by doing 1 minus an eighth. Same exact principle for this one. You know that the distance from here to here is cube root of y, that's this distance, y-axis to here, and that means that this distance has to be the 1 take away the cube root of y. Now this one is the inner function, this one is the outer function. And again, that's because if we're standing on the axis of rotation, the furthest one away, that's the outer one, the closest one is the inner one. Now we also need to determine our limits of integration, and since we're doing a horizontal rectangle, we're going to be differentiating with respect to y, so I need my limits on y. This region starts at y equals 0 and stops at y equals 1. And that should be it. I should be able to set this thing up. Okay, so the volume of this will be equal to pi integral 0 to 1 outer function squared minus inner function squared dy this time, not dx. And then what is the outer function? It's 1 minus y squared. The inner function is 1 minus the cube root of y, and then dy. So you'd have to square this. That's expanding that out. You have to square that. That might be a little weird. 1 minus, I'm going to rewrite that as y to the 1/3 squared, which means times itself. And then when you multiply that out, you get 1 minus 2y to the 1/3. So 1 times 1, then 1 times this is itself. 1 times this is itself. There's -2 of them. Then this one times this one is positive y to the 2/3, because you add the exponents. 1/3 plus 1/3 is 2/3. So that's what this would be. You'd have to distribute the negative sign through, then do all that. And then you'd have a bunch of powers of y, and you integrate using the power rule. No big deal. All right, that was interesting. All right, so the next ones are calculator problems. I'm just going to say let's just set these up. All right, number 19, let's just set it up. Okay, y equals e to the negative x squared, y equals 0, x equals negative 1, x equals 1, and part A says about the x-axis. That's part A. Part B says about y equals negative 1. So let's try this. Again, we've got to graph it. Let's take care of the easy ones first. Y is 0 is the x-axis. X is negative 1, vertical line. X is 1, vertical line. And then finally, what color have I not used here? I have this other one, it's not very good though. I'll try it. Y equals e to the negative x squared. So let's just plug in some points. If x is 0, you get e to the 0, which is 1. So I know at 0 I'm at 1. And then if I plug in, let's say negative 1. Let's just see where I am here. I plug in negative 1. Negative 1 squared is 1. Negative 1. So you get e to the negative 1. E to the negative 1 is 1 over e, which is going to be a small number, which is going to be like this. And then if I do positive 1, the same thing happens. I square it, I take negative, I get the same result, so it's like this. And then as I go out further, they're going to get smaller, so it's going to look something like this. Okay. So now, the region we're talking about is the region bounded by all of those, which is in here. And I want to rotate for part A around the x-axis. So the x-axis is here. I'm going to do a vertical rectangle. I'm going to transpose that over here. Here's my axis of rotation. My rectangle's here. My top function is that e function. The bottom function is going to be the red y equals 0. So the outer radius is the distance from here to here. It's e to the negative x squared. And then the inner radius is 0 because it's not moving. And my limits of integration are negative 1 to 1. So the book asks you to do this and use a computer to integrate it. So you can go to Wolfram Alpha, see if you can figure it out. But really, it's just the setup is what I wanted you to do here. So the volume will be equal to pi integral negative 1 to 1 of the outer squared. So e to the negative x squared squared minus the inner, which was 0 squared, dx. So when you actually do that e to the negative x squared, be careful because what you do here is you multiply these two powers. So negative x squared times 2 gives you negative 2x squared dx. And we do not have a way of integrating that easily. Okay, so we are in trouble if we try and integrate that by hand. But that's why in the book it says use a computer. All right, so that's part A. Part B says we want to rotate around y equals negative 1. So let me show you how that's going to change it. The picture's still exactly the same, except now we're going around a different line. So we're going around y equals negative 1, which is a horizontal line like this. That's our axis of rotation. So when I come over here, draw my x-axis, draw my rectangle, have my curve on top, curve on bottom. Now, if I'm standing on my axis of rotation, which is here, I'm looking out. The outer edge, the outer radius is this, the inner one is this. So the distance here should be pretty easy to get. We know the distance from the x-axis to I don't know, I guess that's a greenish, bluish color, I don't know. This one, that's e to the negative x squared. And then I just need to add this much distance, which is 1. So this will be 1 plus e to the negative x squared. And that is my outer. My inner radius is from here to here. The red one never changes. It's always the same function. So it's just this distance, which is 1. That's my inner. And the limits of integration don't change. So all that's going to change is what's in this integrand. The outer is 1 plus e to the negative x squared minus the inner this time is 1 squared dx. And we would actually have to FOIL that out, but see, we can't integrate this anyway. We have to use a computer to integrate it, so that would be the setup. All right, I like that. I'm just looking here. All right, I had one in mind. It's not in the book. I was thinking about one that was pretty good. Let's say you have y equals x squared sine x. You've got y equals 0. You've got x equals 0 and x equals pi. And we want to rotate this about the x-axis. You know what? Hold on. Let me see if I want that. How about x sine x? That's still going to be kind of a problem. Well, I don't want to work through this one, actually. I want you to think about this one. I don't want to do it. Well, let's just go instead from there to there. Let's go to 1. So I'll help at least set it up, the picture. If x is 0, I'm going to graph the top one. If x is 0, you get this. If x is 1, you have e. And then whatever it looks like in there, you could plug in some numbers, but it's going to connect like that. And so you're looking at a region right in here. What would be interesting about that problem is it's a pretty easy setup, but I would challenge you to try and integrate it. It's a pretty interesting integral to try and do by hand. All right, I won't say any more about that. All right, so I think I have enough time to do one of these weird problems where you have a base that, well, let me just do it. I'm sure I'm going to do one of these in class. Let me look at number 38. Says the base of a solid S is a circular disk. cross sections, that's the end of that sentence. Parallel cross sections perpendicular to the base are squares. And the instructions here are to find the volume. Find the volume. Of the solid. Do you have a minute? Do you have time? Do you have like 5 minutes? I'm going to finish this up.
Fine.
Okay. Which cal are you in?
2.
2? All right. You can come in then. I'm doing a cal 2 problem, actually. Right, so in this problem, they don't give you the actual circle. So if I'm looking from the top down, I have a solid whose base looks like a circle, like this. They're not telling you what the radius of that circle is or anything like that. So I'm going to change the problem a little bit. I'm just going to make this a circle with a radius 4. And that way it'll be a little easier to work this out. So we have a disk on the ground. This is the bottom of this solid. The perpendicular cross sections. So imagine there's some solid above this, and if I come through and I take a slice out of that solid and look at it from the side, it needs to form squares. So here's where we try and get an idea of what this looks like in three-dimensional space. So imagine again, you've got your circle, which is on the ground, which looks like this. That's your circle that's on the ground. And then this is our x-axis, this is our y-axis, so that's laying flat on the ground. If we come through and we take a cross-section of this solid, let me do it in a different color. We take a cross-section that's parallel, so we're running a line parallel to the y-axis, so it's like this, that red line. If we look at that, and we look at that where it's sliced into the solid, it will form a square. That means all sides are the same length. And so what happens is if I take another slice, like a slice that's a little bit closer, like over here, then it'll look like this over here. And notice that that length is not as big as the red one, so the square above it would not be as big. And if I got really, really close, like that, then that square is going to be really, really small, like that. And so if we connect all these together, imagine all the different cross sections together, you're basically going to be connecting their edges together like this. And then they would go back down to 0, and then it would do the same thing on the other side. You go back down to 0. And you've got this weird looking shape. Do my best here to try and draw it. And that's it. That's three-dimensional. It's kind of hard to see. On the back side it curves around, but that's some weird shaped solid that if you take slices and open it up, each slice looks like a square from the side. So the question is, what's the volume of this? So what we're going to do is what we've done before. We're going to take one of these arbitrary slices, and we're going to imagine that slice laying on the ground. Draw my little picture again. That slice laying on the ground looks like this. And then when I come up and make a square out of it, looks like this. So moving all that stuff over here, we've got this picture. Okay, so I want to know what the volume of that little piece is. So if I know this side, and then this, I can find the volume. Well, this side is easy because that's just the width of the rectangle, which is dx. That's always been dx. And then from here to here has to do with the circle itself. It's this distance. It's not the radius because it changes as I go. So I need to figure out the distance from here to here. Well, to do that, I need to know the equation of the circle. And since the radius is 4, I know the equation is x squared plus y squared equals, 16. And so what I'm going to do now is I'm going to solve this for y, move the x squared over, take the square root, and only look at the positive one. So I know that this top curve right here, that right there actually goes this way too, right there. That the distance from here to here is that. That's the y value right there. So the distance from there all the way down, because of symmetry, is double this. So I know that this length right here will be twice as much as this, 2 square root of 16 minus x squared. And if that's what this side is, this side has to be the same thing because it's a square. And so the volume is this times this times this. So the volume of that little sliver is 4, and then the roots multiply, and the roots are gone, so 16 minus x squared, and then dx. You can distribute the 4, but that's not important. So that's the volume of one of the slices. And you want to take all of them up and add them up forever. So you bring in the integral. So the volume of the entire solid will be the integral. Notice I don't need a pi out here because I'm not doing, this is not a solid of revolution problem. This is totally different. I just need my formula. So it's the 4, it's the 16 minus x squared dx. I'm going to add up an infinite number of them, and I'm going to let my x values vary between -4 and 4, because that's how I'm going to move that rectangle back and forth. So -4 to 4. Whatever that is, that's the volume of that solid.